And something was beginning to dawn on us the more of these things we made, because we had a platform, an I/O processor system, that was constant, and we could change the language processor and see what the system performance was. And the more we did it, the more it turned out the performance was pretty much the same as the memory system performance. So the 4 MHz 6502 had a 4 megabyte per second main bus bandwidth. The 68000 has an 8 MHz bus, but it uses 4 ticks for each bus cycle and transfers 2 bytes. So each also had a 4 megabytes per second bus bandwidth. The 32016 similarly has a 4 megabyte per second bus bandwidth, and they all perform the same, no matter how sophisticated the instruction set versus how simple it is. And there's a huge gulf between the 6502 and the 32016, with the 68000 somewhere in the middle. All these chips perform the same, which gave us reason to think. When we built the BBC machine, we had this 2 MHz 6502 sharing its bus bandwidth memory with the graphics system. 2 MHz, 2 megabytes per second for the processor, 2 megabytes per second for the video system. So we could build 4 megabyte systems. If we were going to use a 16 or 32-bit wide memory system, we could build a memory system up to 16 or 20 or 30 megabytes per second. If we could utilize the memory system bandwidth and performance would scale, then we would have something really, really powerful. And the chips on sale, the 68000, 32016, which were the best available, couldn't utilize the memory bandwidth of the machines we could build. The matter might have rested there, but we flew out to visit a company called Western Design Center, WDC. Now, WDC were in Phoenix, Arizona, and they were the company behind the 6502. They were now designing a successor to the 6502, a chip that eventually became the 65ST816, which powered the Apple IIgs, and in fact did power some Acorn machines, which nobody knows much about, the Acorn communicator. And we flew out to talk with them and see what was happening with the 65ST816 design. And we expected that we'd be in some giant American conglomerate. We'd been out to Israel to see National Semiconductor's designing 3216, and it was building this sort of size, staffed full of engineers. We got to Western Design Center, and it was a small building, a bungalow, on the outskirts of Phoenix, Arizona. There were a couple of senior engineers and a bunch of school kids, college kids, who were designing this thing, and we talked to them. And essentially we became extremely convinced that if Western Design Center could design the Western Digital ST816 as a successor to the 6502, we could jolly well design a processor ourselves too. So we left that building utterly convinced that designing processors was simple. Andy Hopper, who I've mentioned before about designing the Ethernet, then sent me a whole bunch of scientific papers that were just beginning to be published about RISC processors. So IBM had just unmasked Project 801, named after the building that the processor was designed in, and which has been a secret within IBM for some time. And they'd actually finished working on 801 in about 1979, but hadn't published anything. Berkeley University had worked on the Berkeley RISC. David Patterson had published papers on the Berkeley system's RISC-1 as quickly as possible. Stanford University, not to be outdone, were also working on a microprocessor without interlocked pipeline stages, MIPS, had also published papers. So all of a sudden, all these pieces of paper landed on my desk. So I read them all. And we started a project called Project A. Project A was just me, Steve Berber and Herman walking around Cherry Hinton in Cambridge talking about instruction sets. The instruction set was designed completely in my head. Steve then knocked things out saying he couldn't implement them, and that's what was the first ARM instruction set. We started the design in late 1983. We taped out the chip and had working chips back by the 26th of April 1985. Making the chip work first time was a big success for us. We'd written an entire reference model in BBC Basic. So this was a queued event simulator that Steve had written in BBC Basic with the entire processor RTL model. And it was RTL, it was doing everything at register transfer model, tracking things through the pipelines. So this wasn't a behavioural one. So that was 808 lines of code. Until recently that existed on a floppy disk inside Steve's garage, but he's now excavated and recovered it for posterity, and this text on the right is actually part of that model. A software team of people under myself had written instruction set validation code. That validation suite is still part of the ARM validation suite at ARM, and each block of the model that Steve wrote in BASIC became a block specification for the VLSI group in Acorn, which was 3 people, Jamie Urquhart, Robert Heaton and Jim Sutton, who implemented the processor. And as I say, it worked first time, which is kind of good. On the right, there's a die photo of the chip. On the left, there is Steve Berber's very first written diagram of how the physical layout would go. The huge block in the middle of the chip, this block here, that's the register file. So outside the register file, there's really not a lot of logic in here. It goes registers, ALU, a barrel shifter, and then the multiplexing together of the load store pipeline and so on out. On the top of it, above the register file decoders. In the top right, things like the priority encoder used for load multiple, store multiple. So that's an ARM chip. The very first one of these things was 25,000 transistors, 12,000 gates. And it was kind of brilliant. And it worked first time, obviously. The pipeline architecture, again, the diagram drawn by Steve is on its left. So what's not so obvious is that we built an entire system at the same time as building the ARM. So on the right, we have an ARM architecture system. So we have an ARM, a memory controller, a video controller, and an I/O controller. We built all of those chips in Project A as well, and they came in at various portions of the time along 1985. For each chip that came in through the door, it was put into its test board, brought up, which for the ARM chip meant we plugged it in as a language processor to the BBC machine, turned it on, ran BBC Basic on it, printed the pie, and opened the champagne. That's how quick the chip bring-up was. Later on, Steve decided that he would try and measure the power consumed by an ARM microprocessor. So he connected the multimeter in series with the power supply in the chip, turned the system on, and the chip was consuming no power whatsoever. The development board that he plugged the chip into had a fault. There was no power being connected to the ARM's power supply lines at all. The processor was actually running from the leakage through its protection diodes around its I/O ring. So the low power of ARM, the thing that is most valued today, the reason why it's in all your mobile phones, was a complete accident. The design team knew nothing about it until it was already inserted. Machines of the architecture on the right we put on sale. So we made a set of ARM2 powered machines. The ARM2 was a minor spin of an ARM1 to add a hardwire